And I recognize Kyoto.
Yes, thank you. So good morning, good afternoon, and good evening for colleagues in Japan. So thanks you, Professor Hecht, for giving us this opportunity to make a presentation before lunchtime. So I am Li Hao from Kyoto University, and sitting on my side is Mr. Nari Nakama. He is our master degree student, and he is part of the contribution of today's talk. Okay, so we are working together with PL for doing some large-scale 3D topology optimization problem. So in today's talk, we will present you some case studies on the topology optimization of multi-physics system. Okay. Okay, let's begin with a brief introduction. So now the topology optimization becomes a very popular words we have heard for several times during the FreeFEM and MMG days. So basically it's a mathematical methods that can optimize material layouts within a given design space. And it has a very high design degree of freedom compared with those of shape and size optimization technique. So here we just recall some interesting applications that we showed in the last year's FreeFEM days. So for example, in these slides, we are doing a mean compliance problem. We start with a full solid material and we run our optimization algorithm to remove those inefficient material. And finally, we end up with those optimal structures. Also, we presented a multi-physics problem last year. So this is a weakly coupled fluid structure interaction problem. So in this year, we're going to show you some more interesting case studies on a thermal fluids problem and a multi-material design problem. Okay. To begin with, let us recall the 4 key ingredients of this workflow. First of all, the cornerstone of this framework is the reaction diffusion equation-based level sets method. The basic idea is that we have an implicit level set function, and we map it to a characteristic function using a Heaviside function. And lastly, using the LSAT material approach, we interpolate the material properties such as thermal conductivity kappa, inverse permeability alpha, using this characteristic function chi. Of course, the interpolation scheme is very important and should be carefully selected. So we follow the lead of Professor Yamada's paper in 2010. So the reaction diffusion equation is used for the evolution of level set function. And we semi-discretize it in a fictitious time. So in this case, by calling the hybrid empathy, we can solve this RDE very efficiently. The second ingredient is the mesh adaptation technique. In the last year or two, we can see a big fashion of level sets methods in the topology optimization field, partly because of the huge improvement of the mesh adaptation techniques. So we can use the body fitted mesh. So with body fitted mesh, we can doing a trimming process. In the context of fluid structure problem, we can extract the fluid and solid subdomains, and we can use the separate equations to modeling the fluid structure system. So for the moment, we rely on the sequential version of MMG 2D and MMG 3D. The MMG 3D is interfaced in FreeFEM thanks to PL's great effort. So we are able to call the MMG within this one single line script. And we can tune in many parameters like this to control the mesh size, gradients, and so on and so on. And also we can use the anisotropic mesh in our framework. So as we introduced above, our methods use LSAT material approach. So we don't necessarily need an explicit boundary. So with this anisotropic mesh, we can handle a much larger mesh size and much more complex geometries. We will show you some multi-material design case later. Again, thanks to FreeFEM PETSI MMG platform, we can use this a centralized version of parallel MMG or a sequential version of MMG 3D in this work. For the 2D case, we just called adapt mesh, which is a built-in function in FreeFAM. The next key point is the parallel computing, because we want to solve not only 2D, but also 3D problems. So FreeFAM is used for discretization of PDEs, and PETSI is used for linear algebra backend. And the physics-tailored preconditioners are used for different PDEs. For example, we use GAMG for LAME, Hybrid for RDE, modified augmented Lagrangian preconditioner for Navier-Stokes. So what's new here in this year is that we use the SLAPC for solving a linear eigenvalue problem. So this is quite new for us. So we will show scalability analysis later on. Finally, we also do some post-processing work. For example, in this figure, we show a heatsink design. The leftmost figure is the optimal solution sampled with body-fitted mesh. Then we convert it into a CAD data, thanks to Mr. Kosi Wano, who is a master student in our lab. Then we can run the simulation in some commercial software, for example, the COMSOL multiphysics or Fluent. Then we can build a prototype using the 3DP. So this process is quite straightforward. Next, let us see some interesting applications. The first one is the natural convection problems. So basically, the natural convection cooling is widely used in those situations where the low noise, low vibration is necessary. For example, the GPU cooling, 5G devices, LED lamps, and etc. Let us consider a cavity in which we have a heat source in red, and the blue domain is the solid region, which is a heat sink. The surrounding air is the coolant. So what we want to do here is to design a compact heat sink structure that can facilitate the natural convection. So therefore, we set the objective functional as a minimization of the mean temperature in the heat source. Also, we have a volume constraint for the solid phase. The governing equation is full Navier-Stokes, which is strongly coupled with the energy equation through a Busnik approximation. Then we need to do the sensitivity analysis. We will not go into the details, but the basic workflow is quite easy. So first, we construct the Lagrangian, including our objective functional, state equations, and volume constraints. So here we have the joint variable, velocity, pressure, and temperature. And then we do the functional derivative with respect to the state variable, velocity, pressure, and temperature. And according to the KKT condition, we can derive the other joint equations. And lastly, the design sensitivity is obtained. Okay, let's see some test examples. First of all, we benchmark our solver against the experimental results of Paolozzini, 2009. So for these, from this comparison, we can have the confidence in our solver. Next, we also write the transient solver to see the flow behavior under different Grashof number. Of course, in FreeFAM, we can use the method of characteristic, but here we want to use the PETSI, so we use the BDF2 scheme for the discretization. Okay, then we can solve, construct the Newton sequence and solve these equations iteratively for each time step. Okay, here we have one video for this. So in this test case, the Grashof number is 1 to the 8. 10 to the 8, sorry, 10 to the 8. Then the flow behavior is like this. So it cannot converge to a steady state. And it will oscillate periodically like this. Okay. And next, let's optimize the heat sink. We have a heat source in red, which is suspended in the air. And we have a coated blue region, which is the design domain for the heat sink. And the coolant fluid is surrounded around the solid parts. Okay, so we have animation also. So we run this optimization algorithm for 300 iterations on a workstation with 32 MPI processors and 128 gigabytes of RAM. The total runtime for this is around 41 hours. And for the last iteration, the linearized fluid system has 3.5 million DOF. Okay. The next benchmark is a lift to drag problem, which is a very classical aerodynamics problem. So we hope to maximize the lift force under a drag constraint. Also, we have a constraint for volume fraction and a center of mass constraint. So the solid body will be fixed in the center of the computational domain. The objective functional is expressed as a boundary integral given by Dr. Kondo, 2012. And similarly, we derive the adjoint equations and the sensitivity as follows, with the corresponding adjoint boundary conditions. So here, what we want to emphasize is that our method is compatible with both body-fitted mesh and anisotropic mesh. So with body-fitted mesh, we can apply the no-slip boundary condition on the fluid-solid interface. With the anisotropic mesh, we introduce a fictitious body force term in the solid phase to stop the flow. Okay, so we run the same algorithm, but using different mesh style. In this case, we have around 700,000 tetrahedral mesh. For the body-fitted case, we use a sequential version of MMG3D, and the remeshing time is 33 seconds. And we use parallel MMG for the anisotropic mesh, and the remeshing time is 2 seconds. So it's a huge improvement. Then we solve the lift to drag problem like this. Okay. The next context of interest is the multi-material design. This part of the work is contributed by Nali Nakayama. So the motivation of this research comes from the people from the automotive industry. So they are asking that if we can put the right materials in the right places. So to do the topology optimization using level set methods, the basic idea is to use multiple level set functions for multiple material phases. For example, in the case of two material design, we have two level set function. The level set function phi1 is to identify the void and solid subdomain. And we use level set function phi2 to identify the solid material 1 and solid material 2. Then we can introduce an additional characteristic function psi, which is a function of chi. And finally, we use this psi to interpolate the elasticity tensor and the mass density. Okay, so the first test case is a mean compliance problem. We have volume constraints for each material phases, and the governing equation is the Lamy system, very classical. To do the sensitivity analysis, in our study, we are using a special derivative, which is called the topological derivative. So this derivative is basically derivative of a shape functional with respect to an infinite small change in its topology. So in the context of multi-material design, such an infinite small change means that one material is replaced by another material in an infinite small circle with the radius of epsilon. Okay. here is the analysis result for the topological derivative. We will not go into the mathematical detail here, but we follow the lead of Professor Novotny's paper, 2003, where he told us the relationship between the shape derivative and the topological derivative. And so in case of two material design, we need to compute 6 topological derivatives with respect to every single material being replaced by another. 1, 2, 3, 4, 5, and 6. And eventually we can update the multiple level set functions by solving multiple times of the level set, reaction diffusion equation like this. Okay, a 2D cantilever benchmark. We want to optimize 3 material phases. So the blue is the most stiff material, such as steel. The yellow is the second stiff one, such as aluminum. And the pink is the softest phase, such as magnesium. Next is a larger scale 3D bridge case. So we have a surface traction applied on the top surface, and the left, right, and of the bottom surface is fixed wall. Okay, we have a short video for this. So in this test case, at the final iteration, we have 2.3 million tetrahedron elements. And this calculation was performed on an iMac using 8 MPI processors with 32 gigabytes of memory. Okay. So finally, the last benchmark is an eigenvalue problem. And the objective here is to maximize the harmonic mean, in which the lambda m is the nth eigenvalue. So similarly, we have a volume constraint for each material phase. And here is the linear eigenvalue problem governing equations. Okay, in 2D case, the left and the right ends are fixed wall. And we have a concentrated mass in the center of domain. Here is the optimal solution, which is quite physically reasonable. And here shows you the first, second, and third eigenmodes. So from the optimal solution, we can see the stiff material is distributed at the left and right ends, where the strain energy is high, and the soft material is placed around the center of a concentrated mass. Okay, so finally we go up to a larger scale 3D problem. Here, as we said, we are using the SLAPC to solve the linear eigenvalue problem. So we do a scalability analysis on a Linux workstation. So for the case of 3 million DOF using 8 MPI processors, the runtime is less than about 10 minutes. Okay. So finally, we do the topology optimization. And we also prepare a short video. Okay, nearly converged. And here is the first to 6 eigenmodes. Okay, so some final words. So in today's talk, we present some interesting applications in multiphysics problems. And our framework is easy to use and highly scalable framework implemented in the free-form PETSI or SLAPC, MMG or parallel MMG. So in our future work, we will do some forced convection problem, fluid to fluid heat exchanger problem, and acoustic metamaterial designs. The wish lists is we hope that the free-form can support some automatic differential toolbox So we don't have to derive the sensitivity by hands every time. And also, we are looking forward to some more turbulent flow solver. So as far as I know, there is only one K-epsilon-based model is available. But if we can have more one equation solver like a Spala-Alamab or the very new Ray-Agawa model supported by FreeFEM, then we can solve a much more complex flow condition. Finally, I would like to acknowledge my colleagues and the professors contributed to this work. Okay, thank you very much for your kind attention.
So we have time for some question, remark and comments. So Pierre, so please go close to the micro.
Can you hear me?
Yes, Pierre.
I have a question with respect to the optimization with the eigenfrequencies.
Sorry, Pierre, I cannot hear clearly.
Is it better now?
A little bit better. Yeah.
Okay.
Yes.
So with respect to the optimization with the eigenfrequency, how dependent is the obtained design with respect to the number of eigenvalue you compute in Scalability? So for example, you compute 6 eigenvalues.
Yes, in the 2D case, we compute 3 eigenvalues, and in the 3D case, we compute 6.
Okay, so if you switch, for example, to 4 eigenvalues in 2D and 10 eigenvalues in 3D, are the design different or mostly the same? Or can you comment on that? Or
I guess it should be different.
do you see large difference or no?
Large difference? So if we switch to 4 eigen or 10 eigen value, is it the optimal solution become very different? A little bit.
You can say, I don't know.
Yeah, I mean, that's something.
Yeah. So it's very impressive computation. So I can add a comment that why there are no automatic differentiation in FreeFEM. We try maybe 10 years ago with Sylvain Oliac, but unfortunately, it was very difficult when you do move mesh and the version will be unstable. So this is a reason why this not occur. But remember, there are an operator which are underscore on FreeFEM, and you want to use this operator to make automatic differentiation. But today is not available. Maybe when I'm very old, possibly I do that. Or, but of course, if somebody have an idea, the people are welcome.
Thank you. Thank you for the comment.
No more question. So we are almost just in time.